Hi, David from Electric Teaching here with part 2 of my video lesson on trying to get the volume after rotating an area about a line. In this case, we've been rotating it about the line equals y equals 6. And we just did the washer method in part 1, and we came up with an answer for our volume. And we want to try to compare this to doing it with the shell method. Whenever you have a washer situation, a shell method may be easier. May not be, but it may give you an alternative of trying to figure it out in case the washer method or whatever was a more difficult method. So sometimes we emphasize doing the shell method as calculus teachers as a better way. So with the washer method, we had a thick washer that was stacked this direction, stacked this way, okay? And we stacked them up from 0 to 2, and the thickness was dx. With the shell method, and I've got another drawing set up down here, so I want to talk about the shell method now. So with the shell method, okay, we are going to think of labels. I think the easiest way to describe this is like labels. Like, for instance, the label on a can. A little quick reminder of geometry basics. The label on a can. Well, if you go all the way around the outside of this, it's 2 pi times the radius r. That's the perimeter equation. And if the can is stacked h high and we unravel this label, it's a rectangle, and the rectangle is h high, and the bottom part is 2 pi r. The width of it is 2 pi r. So the area of this label is 2 pi r h. So quick little review of what a shell or a label is. If you were to stack these via labels that changed heights as you stack them in, labels that you were stacking from maybe the outside in or from the inside out, and you kept thinking about just wrapping this and wrapping this and wrapping this object. That's kind of what the shell method is. So to try to give you, and I'm going to emphasize try to give you a visual of this, I'm working in a 2D world and it's a 3D object, so I'm going to do my best. Please forgive me if I did not able to make this clear. I'm going to look at a sample of a label or a shell inside of this object. I'm going to say about midway through here, there is this shell, this label that I've attached that has this height right here. This height, I should actually draw it from the middle line here. So it has this height right here, and the thickness of it, and you can see it, I'm trying to draw it thick here, is a dy thickness. I wanted to emphasize that right off the bat. The thickness is a vertical thickness, a dy thickness. The shell would go all the way around, have the same thickness over here, and it would come as like a label wrapped right around here, and then again on the back side. I'm kind of only showing the front side of what this is. So this is an interior part of the volume. This is an interior part of the volume. Okay, its radius, you can see it right here off the 6th line, goes all the way down and touches the x squared parabola line. The radius is from the 6th line to touching the x squared line. That's very much like the outer radius we noticed up here. So it's really the length of 6 minus the part that's y equals x squared, and that's really important. So the radius is 6 minus, okay, the y coordinate. Now I want to leave that 6 minus y. The radius is 6 minus the y coordinate because I've already decided the thickness is a delta y. So it's really important that you recognize that since we're in dy, once you get the radius in shell method in terms of y or x, depending on how you're rotating this, then you just leave it. Unlike the disc and washer method, we would determine that the radius is based on a y or a vertical, and then convert it to a dx in that case. So this is a little bit different. The height. Look at the height. It's horizontal. If I was to do another one on the outside, like a really a tiny height one, a smaller height one with a bigger radius label, a shell on the outside here, not fully on the outside, but more towards the outside, you can see that the height is a horizontal. It is basically an x value. So I need the function to be based on y. I need the y equal x squared function to be something I could plug and chug a y into. So I'm going to solve for x here real quick, and if you solve for x, it's a real simple one, plus or minus the square root of y, but we're only going to look at 1/2 of that. So I'm going to take out the minus and say it's just the square root of y. So if I stack infinite shells, either from the outside all the way into the furthest part right here, or from the inside stacked all the way out to the outside, either way, and you'll find that you go different. You'll do it differently depending on the problem. So if I think stacking infinite shells, then it would be all the areas are like this label 2 pi, and then I'm going to stack infinite RH. I'm just factoring the 2 pi out. So I'm basically I'm going to rewrite that. I didn't like the way that came out. Let's do that again. I'm going to stack infinite 2 pi RH's in a dy, a delta y thickness that'll be infinitely small to stack infinite areas. So I've got a two-dimensional area here. I stack them infinitely thick in a sense. That'll give me a three-dimensional volume. I'm doing my best to make sense of this shell method, since I know it is really hard to explain as a teacher, and so sometimes having extra explanations or just maybe hearing it for the second time, even the same words, it'll make sense. So I'm doing my best to really give a thorough explanation. I'm sorry if the video is going a little long and you just want to get the mechanics of this. I really believe in teaching an understanding of this whole shell method being wrapped infinite times, or stacked, and not so much stacked, but layered infinite times from the outside in or the inside out, either way you want to think about it. Okay, so let's go ahead and do the mechanics now. 2 pi integral, well, it's a dy. What are we integrating from here? We're integrating, we got to be careful here. I'm going to stack it. I think the easiest way is from zero all the way into the 4 line. I don't want to go into the 6 line because I don't have any labels in there. I have no thickness in there. I have no area in there. It's hollow. So I'm going to go all the way up to the 4 line. So in the y sense, it's 0 to 4. And then the r is 6 minus y. And the h is root y. I always want to double check that these radius and heights make sense with my 0 and 4 inputs into the integral. So at 0, I should have a 6 radius. Check, I do. I should have no height, and check, I do. If I put in 0, I get no height and a radius of 6, so it does check. Same thing at 4. At 4, I should have a radius of 2 with a height of 2. And if I put in a 4, I get a radius of 2 and I get a height of 2. So before I even do this problem and waste a bunch of time, if it's wrong, I don't want to waste all that time. Before I do all this work, I want to be sure I've set up the integral correct. Too many times, this is the harder part, and you already know how to do integration, so that's the easier part, hopefully. And therefore, you don't want to mess up this first part. Okay, I think I've got it set up right. 2 pi. Okay, let's clean this up a little bit. There is no product rule for integration, so I've got to simplify this somehow, or otherwise I'm really in trouble here and I can't do it algebraically. So I'm going to think of this as y to the 1/2 distributed. 6y to the 1/2. Okay, 6y to the 1/2 minus, let's see, y to the first times y to the half. So that's a total of 1.5 y's multiplied, or y to the 3/2. Again, this is dy. Now I can integrate 2 pi. And let's see, if I add 1 and then flip and multiply, it's the way I try to teach my students. So let's add 1. I'm going to put the 6 out here. Add 1, and it's going to be 3/2. And if I flip and multiply 3/2, I'm then multiplying times 2/3. Okay, minus, let's see, same thing. Add 1, that would be 5 halves. 2 over 2 is a 1, so add it, common denominator, 5 halves. 2 fifths, flip and multiply. Okay, I didn't think I need that extra parentheses. Let's get rid of them. 2 fifths, 2 fifths. Clean that up a little bit. Sorry about that. So now I can start thinking about the plug and chug parts, because now I can put in a 4 and a 0. And if I've said this enough times in these videos as I'm teaching calculus, please, most of these are set up to be not needing a calculator. Don't use a calculator unless you absolutely want to check, even if your teacher allows you to. I'm trying to develop your brain to be a strong, confident, number crunching brain out there. So please, you'll find that you can do these. You have the experience. 3 and the 6 cancel, leave a 2. So this is 4 times y to the 3 halves. Y to the 3 halves. I wanted to clean that up a little bit before I plug and chug. This one's fine. It's ready to go. 2 pi on the outside. 2 pi on the outside. On the inside, if you plug and chug a 4 into this using the fundamental theorem of calculus, and then subtracting the plug and chug of 0, well, 0 is going to be 0, so I don't have to worry about that. The answer is really the plug and chug of 4 times the 2 pi. So if I plug and chug a 4, the 4 then is always do the bottom root first. It makes it easier. Go small first, as I like to tell my students. Make it smaller first. 4 square rooted is 2, and 2 cubed is 8, and 8 times 4 is 32. See? Wasn't that hard. 4 inside of here. 4 square rooted, 2. 2 to the 5th, 32. 32 times 2, 64. So minus 64 over 5. Okay, same thing. Don't need a calculator here. 5 goes into 60, 12 times? Double check it. So that's really just 12 with a 4 left over, or 12 and 4 fifths. Okay, so if I'm going to subtract 32 from that, then it's 2 pi times, don't lose the 2 pi, 32 minus 12, well, that's 20, minus another 4 fifths, that's 19 and a fifth. 19 and a fifth. Double 19 is 38, double a fifth is 2 fifths. Put in the pi, and you will see we have the exact same answer we got with the washer method. And in this case, I tend to argue that equally these are both have their difficulties, and neither one is simpler than the other. But there are many times that you'll be able to do a shell method or a washer method, and you won't be able to do the other one by hand. Sorry about that. Lost the screen there for a second. So I hope that I've helped. I'm David from Electric Teaching, and this concludes, I think, the volumes that I'm going to do in my calculus stuff. So good luck with your next homework or test.